So we're basically going to be looking at this chapter, metals, I think chapter 12, in chemistry, metals and non-metals, and alloys. Part 1, we look at metals and non-metals. Part 2, we look at extractions of metals from their ore. Okay? Now let's quickly take a look at this. In the periodic table, you're going to have different elements which are arranged as shown in this periodic table. You can see these blue ones, they are the metals. And you see the yellow ones, they are the non-metals in the periodic table. These purple ones, they are the semiconductors, what you call the metalloids. Okay? They are also called semiconductors. So the metals are a lot. But group 1, group 2 form the real metals, right? Group 1, group 2, and some elements in group 3 form the metals, right? Now let's take a look at that. Group 1, group 2 form the normal metals. But between group 1 and group 3, there are metals that have been arranged in the periodic table, which are called the transition metals. Which are called what? The transition metals. Which are called the transition metals, right? Now these transition metals, what do they do? What do we use them for? What do they do? These transition metals, first of all, we say they have some characteristics which makes them a little bit different from group 1, those of group 1 and group 2. Group 1 and group 2, you can begin to talk about the properties. They ask you to give the properties of group 1 and group 2 metals. You can begin to talk about their boiling point, high metal point, high density, and so on and so forth. For group 1 and group 2, they conduct electricity, which some of you wrote in your exams. But this is not it when they ask you for transition metal. They ask you for transition metal, simply tell that they are transition metals. They are used as a catalyst. They are used as what? Catalyst. They can be used as catalyst. They form color compounds, and they form variable oxidation state. They form what? Variable oxidation states. They form variable oxidation states. So we need to have this idea at the back of our mind for metals and non-metals, and we need to understand how the periodic table is formed. This is group 1 in the periodic table. You can see lithium, sodium, potassium, rubidium, and calcium, and fratrium. So you can see all these elements which form the group 1 metals, and you have the group 2, beryllium, magnesium, calcium, tritium, barium, and radium. So you can see these are the group 2 elements. Between group 2 and group 3 in the periodic table, here is group 3. Now between group 2 and group 3, you have transition metals. You have transition metals. Is that okay? And then you have what we call the metalloid, or either you call them metalloid or semi-metals. You can call them semi-metals. They are not fully metals, neither are they fully non-metals. They are called semi-metals or metalloid. This boron, silicon, germanium, astatine, all of this tin and lead, polonium, all of these are called the metalloids. Then the non-metals like carbon is a non-metal, nitrogen is a non-metal, phosphorus is a non-metal, oxygen is a non-metal, sulfur is a non-metal, fluorine is a non-metal, chlorine is a non-metal, neon. Neon is group 0 or group 8. These are noble gases. Group 8 or group 0 are noble gases. They don't need to react because they already have 8 electrons in their outermost shares. They already have 8 electrons in their outermost shares, so they don't need to react. So you can see these ones, they have 8 electrons in the outermost share. They are in group 8 in the periodic table. Okay, now let's begin to look at it. We already said the ones on the left, they are the metals, whether group 1, group 2, or the transition metals, and some elements in group 3, from aluminum, germanium, and all of this one, they are all metals. They are all metals. All this blue color or whatever color you want to call this, they are all metals. So this color are metals. You can see in this Earth, on this planet Earth, there are so many metals. Right? Metals are more than non-metals. Okay? So we have the metalloid, the one we call semi-metals, and then we have the non-metals, which are the yellow ones. Now let's move on quickly and look at the physical properties of metals and non-metals. First of all, let's take a look at the properties of metals. Metals are able to conduct heat and electricity. Why? Because they have free mobile electrons. Why are metals able to conduct electricity or conduct heat? Because they have a free mobile electron. Because metals have free mobile electrons. Because they have free mobile electrons, so they are able to conduct electricity. Because metals they have free mobile electrons, therefore they are able to conduct electricity. They are able to conduct electricity. Is that okay? Okay. Because they are free mobile electrons, they are able to conduct electricity. Free mobile electron, or what you call delocalized electron. What you call the delocalized electron. Free mobile electrons. So metals, they have free electrons. You know, the particles are closely packed together, right? So when you talk about arrangement, they are touchy, particle touch. So they ask you for the structure, for the arrangement of metals in chemistry in the exam, say particle touch. They are particle touchy, and that's for the arrangement. And they're in fixed position, and when they're heated, they vibrate. Okay, their movement is about vibration. They don't move. They don't move from place to place. So metals can conduct electricity because they can vibrate and have free electrons to carry the charge, from a place to place. So we call them the delocalized electrons. Metals have what we call the delocalized electrons, or free mobile electrons. As a result of that, they're able to conduct heat and they're able to conduct electricity. That's number one. Number two is that metals are malleable. What do we mean by malleability? We mean metals can be hammered. They can be hammered. They can be hammered, and they can be beaten to different shapes. Malleability is the ability of a substance to be beaten to different shape. So that substance can be hammered. You can hammer it. You can take a hammer and hit it and change the shape, and use hammer to hit it to change it to another shape. So that ability or quality is called malleability, malleable. So metals are malleable. Not only that, they are ductile. Another properties of metal is that they are ductile. What do we mean by ductility? By ductility, we mean that they can be drawn into a wire. When you say metals are ductile, you're saying that they can be drawn into what? They can be drawn into wire. Because, for example, the copper wire, the aluminum wires, they are from metals. They've been able to be drawn to wire. They've been able to be used to make wire. So that ability is called ductility. Now let's go quickly to the next one. And now, why are they able to be drawn into wire? Because they are in layers, right? Because they form layers of positive metal ions, right? And the structure also, they can slide over each other. Now, usually they have high melting points and high boiling points. So metals have high metal. The fourth one, if we're not mistaken, this will be the fourth quality. This is the first one. Heat. Here you are actually combining two, because metals are able to combine heat is a property. Metal are able to conduct heat is one property. Conduct electricity is another property. So here you have two properties, because you're talking about their conductivity, thermal conductivity. That's one property of metals. Electrical conductivity, the flow of electrons, is another property. So this is the third one, this is the fourth one. And here, melting point is the fifth one, boiling point is the sixth one. Okay? So this is for this one. Now we move on to non-metals. Let's quickly take a look at that of non-metals. The properties of non-metals. Non-metals, they do not conduct heat, cannot conduct heat, and cannot conduct electricity. Why? Because they don't have the delocalized electrons. They don't have the delocalized electrons to carry the charge from one spot to another spot. So because they don't have delocalized electron, they cannot conduct electricity. Is that okay? Because the electrons evolves, because of the electrons are evolved in covalent bonding. It's not ionic bonding. They don't have ionic bonding. Non-metals, non-metals combine with themselves to form covalent bond. They don't form ionic bond. Ionic bond is between metal and non-metal. Ionic bond is a bond that happens between a metal and non-metal. And non-metals themselves alone, they form covalent bonding. Remember that. We've treated that already. So they form covalent bonding. So they cannot form ionic bond. But there's an exception. One non-metal, there's an exception. Carbon is a non-metal. We've shown you from the periodic table. Carbon, you see, it's going to be a yellow color. Carbon is a non-metal. And the allotropes of carbons are diamonds and graphite. The allotropes of diamonds are graphite and diamond. This graphite is a form of carbon. That's the meaning of allotropes. It's a form of carbon. Another form of carbon is a diamond. Now, diamond do not conduct heat or electricity, so we're not going to bother. We just treat it as a non-metal. But Why there's an exception. Graphite, which is a form of carbon, is able to conduct electricity when molten. Is able to conduct electricity when molten. Because why? Because graphite, if you study graphite, they are arranged in layers. Graphites are arranged in layers. Each carbon is covalently bonded with 3 other carbons, but they are arranged in layers. They are arranged in layers. There is a strong bond between the carbon atoms, but there is weak intermolecular forces that joins the layer. Weak intermolecular forces that can be broken that joins the layer. So hence, graphite as a form of carbon, allotropes of carbon, is able to conduct electricity only when it's in molten state. Only when it's in molten state. Is that okay? So that's the only exception. Now, non-metals, they are brittle. They are not, where you say metals are malleable, you say non-metals are brittle. They can easily break. They can easily, that's the meaning of brittility. They can easily break. Okay? Non-metals are brittle. They can easily break. Is that okay? Okay, so they are not, they cannot be drawn to wire, they cannot be beaten to different shapes. When you hit them, you only break it then. That's it. Okay, now we go to another one. They have low melting and low boiling point. Non-metals, they have low boiling and low melting point. Because they are not metals, of course, they are not, the particles are not closely super packed together, and most of the times they are a little bit far, particles are a little bit far apart. So they have low melting point and low boiling point. Low boiling point. Is that okay? Many non-metals are gases. They are not solid. You know, metals are mostly solid except bromine. Except bromine, right? Is it only bromine? Bromine and mercury, right? Okay, so these are the ones that are not except with the exception. Most of the metals are solids. Okay, but most of the non-metals are gases, like hydrogen gas, oxygen gas. Most of the metals you can think of, like helium, all of them, most of them are gases. Not all. Most of them are gases. Most of the non-metals are gases, except bromine. Bromine is a non-metal. We can go to the periodic table. Bromine is a non-metal, but it's not a gas. Bromine, if you look at group 7, you know bromine, the halogen family, they are in group 7 of the periodic table. The fluorine, the chlorine, the bromine. See, bromine is a non-metal. So it's not a gas, it's a liquid. Bromine liquid. Bromine is a liquid. Is that okay? Okay. The rest are, most of the other ones are gases. Most of the other ones are gases. Is that okay? So because they are what they are, they are not so strong. They have low melting point, low boiling point, and so on and so forth. They have weak intermolecular forces joining them together, okay, and so on and so forth. So let's say they have weak bond and weak intermolecular forces joining them together, except diamond. Diamond is the hardest substance on Earth. Except diamond and silicon dioxide. Okay, these are the only two that are very hard, very hard. The structure of diamond is so unique. Diamond is the hardest substance. It's even harder than metals that we are describing. This is the irony of life. Okay, non-metals are very weak. They are they are not hard, but it has one exception: diamond. Okay, now. Let's take a look. All the one we've talked about, they are called the physical properties. They are called the physical properties. They are called what? The physical properties. Now let's take a look at the chemical properties of metals. What do we mean by chemical properties? We're talking about the reactions. We're talking about the reactions that they undergo and to form a permanent change, to form a new product, a permanent change, a new product. These chemical properties of metals. Now we start with their reaction with water. Okay, you know what? Metals react with water. That's a liquid. Metals also react with steam, hot water. So the product they form when they react with water, cold water, and when they react with hot water, steam, is kind of a little bit different. So let's pay attention to these two differences. Now we start with the first one: reaction with metals with water. These are chemical reactions because the new product will be formed. A completely new product will be formed. Now when we take a metal and react metal with water in this case is liquid. We're talking about normal cold water. Okay, this water is a cold one. We're talking about cold water in this case because we have cold water and hot water. Okay, liquid and gas. The hot water is called gas, it's called steam, and the cold water is liquid. So when metals react with cold water, they form metal hydroxide. Like in one of the chemistry exam, like the paper we saw, is that they say calcium react with react with water. But you couldn't write they say you should write equation for it. Calcium react with water. Look at it. This calcium. This question was in the paper, the chemistry exam you guys did, and you have to be able to. It's in your past paper. Go check. Calcium react with cold water is going to form calcium hydroxide and hydrogen gas. So when metal react with water, they form metal hydroxide. So it depends on the metal. If it's calcium, it becomes calcium hydroxide. If it's zinc, it becomes zinc hydroxide. If the metal is sodium, it becomes sodium hydroxide. If the metal is potassium, it becomes potassium hydroxide. So it depends on the metal. So when metal react with water, it form metal hydroxide and hydrogen gas and hydrogen. Okay, we form metal hydroxide and hydrogen gas. For example, a good example is calcium. Calcium is a solid because it's metal. Most metals are solid. So calcium react with water, which is liquid, cold water. Once it's liquid, we are talking about cold water. React with cold water, it will form what? Calcium hydroxide. Hydroxide is OH. Okay, this hydroxide. This hydroxide. This is how we know alkali. Hydroxide. Okay. If they ask you to define in the exam, also I saw in the exams they say define an acid. Many of you don't know how to define acid. Acid, just simply say acid is a protodonor. Acid doesn't. They say acid is a chemical. No, acid is a protodonor. That's hydrogen, and it produces. Another way to say it is a substance that produces hydrogen ion as the only positive ion in aqueous solution. If another way you want to say it, you say because hydrogen plus is called proton. This hydrogen plus is called proton. So you can just say acid is a protodonor. As simple as that for your definition. Acid is a protodonor, and alkali or base is a protoacceptor. Protoacceptor. One is a protodonor, the other one is a protoacceptor. Finish. This is what you should say. Short answers. Precise short answers. Acid is a protodonor. Alkali or base is a protoacceptor. Or another way to define alkali, you say is a substance that produces hydroxyl ion as the only negative ion in aqueous solution. Hydroxyl ion, sorry, this minus is outside to show it's talking to both. Hydroxyl ion as the only negative ion in aqueous solution. But if you don't want to write those long stories, you just say an alkali is a proton acceptor. Proton. The normal proton you know, okay, is a protoacceptor. Just say protoacceptor, meaning it accepts is a substance or a chemical, like you said, that accept hydrogen plus. Protoacceptor for alkali, protodonor for acid. That's it. Okay, now let's move on. We take note. The first chemical reaction, chemical properties of metal, is that they react with water. Metals react with water. If they react with cold water, they produce metal hydroxide plus hydrogen gas. What if they react with hot water, steam? If metal react with hot water, what will they produce? They will produce metal oxide. They will not produce hydroxide. Please take note of this. When they react with hot water, they react with steam, they're going to produce metal oxide and hydrogen gas. But when they react with cold water, they will produce metal hydroxide. Metal hydroxide, like the name here. When they react with cold water, you see I wrote cold here to tell you this water is cold water. When they react with cold water, they produce metal hydroxide and hydrogen gas. Now, this is an example to demonstrate what we are saying. You write calcium, you must write the state symbol. Calcium, you put in brackets small s to show that it's solid. React with water. Water is H2O. This 2 is for balancing. Okay, this one you're going to do it in the end. Okay, you write H2O first. You write liquid L. You put it in bracket to show that it's a liquid. It will produce what? Calcium hydroxide, CaOH. But this one will be, there will be 2 here. Why is this 2 here? Why not just CaOH? Why do we do this? Okay, the reason is that you know the calcium has 2 ions, right? 2 ions positive, so plus 2. Calcium has plus 2, right? OH has minus 1. OH has minus 1. So I write it here. You should learn how to do this so that you can always write the compound that is formed when substance react. Okay. So when they react, in chemistry we cross multiply this and this. Okay, we cross multiply. So 1, you don't use the sign, you don't use the plus and minus, just use the number. You say 1 times 1. Here means 1. It becomes calcium, Ca only. It becomes Ca only. Then 2 times OH. Why do we put bracket? Because the 2 is talking to the OH, both of them. So if I write OH, and I write this 2, this 2 is now cross multiplied to this side. If I just write 2 here, it will look as if it's talking to only hydrogen, right? It will look as if it's talking to only hydrogen. Are you with me? Okay, just a minute. Our internet is laggy. Okay, connection restored. If we write 2 here, okay, every time this happens, we lost some writings. This calcium, this is the hydroxyl ion, okay? Now, I say cross multiply this 2 to this side. If you write the 2 here, it will look as if the 2 is only talking to OH. For the 2 to talk to both oxygen and hydrogen, you put the bracket. Then you write the 2 here. So it means this 2 is talking to these 2 elements, these 2 atoms. Okay, so you have calcium hydroxide like this. So this is how we got the calcium hydroxide and these 2 here. It's an aqueous substance. It's aqueous because it's an alkali. It's an alkali, so it's aqueous. Right? So you write the aqueous plus hydrogen gas produced. Because every time metal react with water, hydrogen gas is given. How do you know? Because it makes a pop sound. It makes a pop sound. Okay? Right? No, it's oxygen. Hydrogen make what? The test for hydrogen. When you bring it close to a glowing split, it makes a pop sound. Oxygen rekindle a glowing split. Oxygen is to rekindle a glowing split. Hydrogen will make a pop sound. How do we know that hydrogen gas was produced? Because if you bring any glowing split to it, it will make a pop sound. If you bring anything like a burning match to this reaction, it will make boom. To make boom, make such a sound. So we know hydrogen gas is produced as well, not only calcium hydroxide. Okay, so this calcium hydroxide is an alkali, and hydrogen gas is also produced. That's for that reaction. Now let's move on. When metal react with steam, steam means what? The hot water. Steam like water vapor. When metal react with steam, it produces metal oxide, not metal hydroxide now. With cold water, it produces metal hydroxide and hydrogen gas. With steam, it produces only metal oxide. Take note, this will be in your exam. Definitely, they are there. Either in multiple choice or in structure paper 4 or in paper 6. So when metal react with steam, it produces metal oxide and hydrogen gas. Now this is an example. We take zinc as a solid, which is a metal, react with steam. Once you see G, gas, it means it's a steam. The water is steam. So how do you know it's cold water is going to be? You can see this equation, you see G here, which means it's a gas. When they say gas, it means it's a steam. Water is a steam, it's a water vapor. So when they react, it will form what? This O will combine with this zinc to become zinc oxide. And zinc oxide is a solid. Then this remaining H2 will be this hydrogen gas. Will be this hydrogen gas that is produced. How do you know there's hydrogen gas? You bring a glowing split to it to make a pop sound. Is that okay? So that's for reaction with water. Now, for metals, which other chemical properties they have? They react with acid. Now, let's describe their reaction with acid. Okay? Here, the examples did not elucidate the various type of acid. But maybe we can take a look at some of the acid. Okay, but let's first of all take a look at the one we've shown here. Most metals react with acids such as hydrochloric acid. And when acids react with metals, they will produce hydrogen. They will produce a salt and hydrogen gas. Okay, we're going to take a look at example. Metal plus acid will produce salt and hydrogen gas. Just now we produce metal hydroxide or metal oxide and hydrogen gas. But now we produce a salt and hydrogen. How? When iron, we take iron as a metal, react with hydrochloric acid, we produce what? Because iron is higher than hydrogen reactivity series, it will displace hydrogen. It becomes iron chloride. Now, how do we get this, write this formula like this? You come here, you write the ions. Iron has 2 plus. Iron has 2 plus because in group 2, right? The periodic table. Iron has 2 plus. It's a transition metal. Okay, good. Iron is a transition metal. Yeah, thank you. It's a transition metal. So they have variable number of 2. So chlorine has -1, right? Chlorine is in group 7, so it's looking for 1 electron to complete 8. So it has -1. It's looking for 1. -1 means it's looking for 1 more electron to complete 8. If you have -2, meaning you're looking for 2 more electrons. Okay, chlorine has -1. So we cross multiply this times this 1. We're not going to use this plus or minus. We just use the number this times this. So you have iron 2 chloride like this. Fe 1 times iron become Fe only. And then chlorine, Cl times 2 becomes Cl2. It becomes Cl2. So this is how we get this iron 2 chloride. Okay, this is how we get this iron 2 chloride. It's a salt. Metal and chloride, metal and carbonate, metal and sulfate, metal and nitrate, they are all salt. It becomes salt. Okay? Okay, so this forms the salt and hydrogen gas. This hydrogen becomes this hydrogen gas. Okay? So this is only when we react with hydrochloric acid. What we react with, let's take, we say magnesium react with sulfuric acid. What do we get? We get sulfate salt. Magnesium plus sulfuric acid. Sulfuric acid is H2SO4. Sulfuric acid is what? H2SO4. So when we take this to react with magnesium, sulfuric acid, we get what? Magnesium sulfate. That's the salt we're going to find. So the kind of salt you produce depends on the acid. So since you are reacting with sulfuric acid, you're going to produce what? Sulfate salt. So it becomes magnesium is higher than hydrogen reactivity series. Magnesium is higher than hydrogen reactivity series. It will become what? Magnesium sulfate. It will displace hydrogen to form what? To form magnesium. This magnesium will kick hydrogen out from here because it's higher in the reactivity series. So okay, you're going to look at all the reactivity series and see the arrangement of metals. Which one is higher? We're going to, in part 2, we'll be showing you. Is that okay? The reactivity series. So magnesium is higher. It becomes magnesium sulfate. You come and you tell this hydrogen to stand up, and he will sit in that position. It becomes magnesium sulfate. This magnesium sulfate is a salt. Okay, this magnesium sulfate is a salt. Plus what? Hydrogen gas. Now, why do we just write MgSO4? Why do we write MgSO4? This MgSO4 is aqueous because it's a salt, it's aqueous. So this is state symbol. When you write equations, you learn to write their state symbols. Okay? So we write the state symbol. This one is also aqueous. It's an acid, it's an aqueous. Okay? If something is solid, except something is solid, you write solid. If it's liquid, you write liquid. If it's gas, you write gas. Other than that, then it's aqueous. Magnesium is solid, you write solid here. If you don't do this, you not get the full marks in your chemistry. There, hydrogen is a gas, you write gas, you put them in bracket. All the state symbol, you must put them in a bracket. Okay, so when you do this, you get, and you balance your equation, you get all the full marks that I said that question deserves. Okay, now this is this. How do we do this? Magnesium has 2 plus. Why did you write it plus? But remember, sulfate has 2 minus. If you cross multiply, 2 comes here, 2 comes here. Now it will become something like this. We don't write that. We simplify to the smallest unit. It becomes something like this. Mg2SO42. It will be something like this. SO4. You put every of this one in bracket because this sulfate has -2 ions. Okay, so SO42. So when you cross multiply, this is what you get. These 2 we cancel these 2. That's why it remains like this. Is that okay? That's why it remains like this. Okay, that's the salt that is formed when you react with sulfate salt. What if we react with, when we take a nitric acid to react with any of the metals? Let's say sodium, for example. Sodium plus nitric acid HNO3. We're going to study acid-base assault so that you refresh yourself with acids. Okay? HNO3, this is called nitric acid. Okay? This is called nitric acid. And when this happens, metal plus a nitric acid, you form a sodium nitrate. Okay? You form sodium nitrate. Like this. Sodium nitrate, which is a salt. Sodium nitrate, which is also a salt. And hydrogen gas will be formed, will be produced. So in a nutshell, sodium nitrate plus hydrogen gas. This one is aqueous because it's a salt. It's aqueous. You write the state symbol for each of them. And you put the state symbol in the bracket. Then plus hydrogen gas. Hydrogen is a gas, so you put G as the state symbol, H2G. Okay, you can balance the equation. That's up to you. Balancing of equation is something you should know before now. Okay, this is AQ, aqueous. You put it as the state symbol for this. And sodium is solid. You put the state symbol as solid for sodium. Is that okay? So this is how you write equation and check their balance. Why is this one Na? Because sodium has 1 plus, NO3 has 1 minus. So when it 1 and 1, it remains the same. Is that okay? This is why the formula is like this. Now this is one of the properties of metal reacting with acid. We talked about reaction with metals. We talked about metals reacting with water, both cold water and hot water. That's the first reaction. The second reaction, I went to the reaction with acid. I've used different types of acid. I've used hydrochloric acid. When we took iron reacting with hydrochloric acid to produce iron 2 chloride and hydrogen gas, we took sodium reacting with nitric acid to produce sodium nitrate and hydrogen gas. We took magnesium reacting with sulfuric acid to produce magnesium sulfate, salt. This is a salt, this is a salt, and this is a salt. Okay, the type of salt that is produced depends on the type of acid that is used. Okay, now that's that for that. Now let's go to the reactions with the metals reacting with oxygen. Quickly, this one, quickly we just metal react with oxygen to form metal oxide. Okay, because oxygen is just O2. When metal react with oxygen, they form what? Metal oxide. They form metal oxide. Copper react with oxygen because copper 2 oxide. Right? Now let's go to uses of metals. What do we use metal for? Aluminium is used for so many things. Aluminium is used for because it sits above hydrogen in the reactivity series. It means that it's a very reactive metal. We have the first 5. We're going to study in the reactivity series the first 5 metals that are very reactive and why they be extracted using electrolysis method. We're going to describe that in our part 2. The first 5 metals in the reactivity series starting with potassium, sodium, calcium, magnesium, and so on and so forth. All the first 5 in the reactivity series and why we use the electrolysis method to extract them. And we say aluminum is used for making aluminum oxide, they are used for making the body of airplane, they are used for making electricity wire, they are used for making can, they are used for making saucepan, they are used for making, and so many things. Now let's take a look at them one after the other. Aeroplane bodies, we use aluminum to make the body of the aeroplanes. We use aluminum.
7. That's scam.
We use aluminum to make the body of aeroplane, right? Now, why? Because they have high strength to weight ratio. Although they have low density, but they have what we call the high strength to weight ratio. Their strength, compared to the weight you put in them, is very strong. Aluminum, even if it's not so, it doesn't look strong. When you put things on it, it's able to withstand the weight. We call it strength to weight ratio. A very good one, even if they have low density. Number 2, aluminums are used to make overhead cable lines. You know the transmission line from one state to another state or from country to another country? We use aluminum. The copper wire is just to the one we use inside the houses. Okay, but for long transmission, we use aluminum wires. So they're used for making cable wires for long transmission. They're very good they have what we call good electrical conductivity, even though they have low density. They are used for making saucepans. Why? Because they have good thermal conductivity. They have good thermal conductivities. They are good conductors. So you use aluminum to make pan for frying things. And then they are used for making food cans. They are used for making food cans because they are not toxic. In fact, one of the reasons for making can is that can for drinks is because they have very high resistance to corrosion. They don't easily rust. They have very high resistance, or like iron. You don't use iron to make can now to keep your drink or to make your food can, because the iron will rust and your food will poison your food. You will eat food poison. But aluminum, they're very resistant to corrosion and very resistant to acid. So you can use it to save food, preserve food for a long time. They're also used for making this plastic. They're not plastic like plastic. I'm saying, what to call it? You use it to wrap food. Aluminum foil. They are used for making aluminum foil for wrapping food and kind of wrapping things and preserving food and so on and so forth. Okay, now let's go to copper. Right, we've described aluminum. What is copper used for? Copper is a good conductor, so it's used for conducting electricity, right? Copper sits below hydrogen in the reactivity series, which means it's unreactive metal, right? Compared, like not so reactive. Now the use of copper relates to its properties. It's an excellent conductor, so it can be drawn to wire and used for making electrical conductors. Okay, that's the big one. Okay, now these are the conductors, these are the copper wires. The conductive part is this one. All these are isolators to cover it, so that you don't get electrocuted. Now let's take a look at the particular uses. They are used for electrical wiring, for wiring your house, because they are good conductor of electricity and they can be drawn to wire also. And then they are used for making pots and pans. Copper, you use them for making pots. Okay, because they have good thermal conductors, and they are reactive and they are malleable. They are used for making what we call the water pipes. They are used for making pipes because they are not toxic. Okay, they are used for surface in hospitals. Antibacterial properties, they have that. Okay, now let's move to alloy. Now before we move to alloy, let's quickly take a look at our tutorial. 1 minute tutorial. Okay. Okay.
In this video, we will be looking at the topic of alloys. An alloy is a mixture of two or more metals, or metal with a non-metal. At least one of the elements must be a metal. Here, element X represents the metal, and element Y is the other element. Examples include steel, which contains iron and carbon, bronze, which contains copper and tin, and brass, which contains copper and zinc. Alloys often have properties that can be very different from the metals they contain. For example, they can have more strength, hardness, or resistance to corrosion or extreme temperatures. These enhanced properties can make alloys more useful than pure metals. For example, aluminium is mixed with copper, manganese, and silicon for aircraft body production, as the alloy is stronger but still has a low density. Remember that an alloy is not a compound. It is a mixture, as the different elements are not chemically bonded together. To understand why alloys are used instead of pure metals, we need to look at their structures. We will use copper as an example, but remember that pure metals all have a similar arrangement of the metal ions. If a force is applied to the regular lattice of a pure metal, the layers can slide over one another, meaning that metals are malleable and ductile. Malleable means the metal can be hammered into shape, and ductile means the metal can be drawn out into a wire. However, if we look at an alloy such as bronze, we can see that the atoms are different sizes, and the regular arrangement of the pure metal has been distorted. This means it is much harder for the layers to slide over one another. If you were asked in a question about the properties of an alloy compared to a pure metal, remember to write down that the atoms in an alloy are different sizes. Let's now have a look at some example exam questions which are about alloys. This question asks you to explain why steel alloys are used in preference to iron. This means that you must give a reason for steel being used instead of iron. We know that alloys have more desirable properties, and we need to compare the two by using words like stronger, harder, or more resistant. Make sure you use these words and compare the two materials for the mark. The second question is asking for a use of stainless steel, which is a common question. Here, you just need to give one use for 1 mark. Make sure you know at least 2 uses of each of the alloys you need to be aware of, just in case one is already given in the question. This question comes up a lot, but is given in different contexts. The main point being asked about is why alloys are stronger than pure metals. As we have seen in this video already, we know that the structures are different, and this has an impact on their properties. There are 3 marks on offer, so 3 points should be made. The question is asking you to make the comparison between a pure metal and an alloy, so you must make reference to both materials. For the first mark, you need to say that pure metals have a regular lattice arrangement, or all the atoms or ions in a pure metal are the same size. For the second mark, you need to say that the alloy contains atoms that are different sizes, and this will disrupt the arrangement of the layers. This means that the layers in an alloy can no longer slide over each other as easily. This will now score you your 3rd mark. In summary, you need to know that an alloy is a mixture of 2 or more metals, or a metal with a non-metal. Alloys are used instead of pure metals as they are stronger or harder, more resistant to corrosion, and to extreme temperatures. Alloys contain elements of different sizes that distort the regular structure of a pure metal. Don't forget to check out all our other fantastic revision resources here at Save My Exams.
Okay. Now we've seen the alloy, the difference between alloy and metals, right? Pure metals. Alloy is a combination of 2 or more metals. Remember, this is not a chemical combine. It's not a compound. It's not like you chemically combine it and you form a new product. Even though for the other one, you are taking a metal and a non-metal to make a compound, right? Here we are taking a metal and a metal, most of the time a metal and a metal. So we are blending them together. So it is called alloy. So alloy, it's quite a little bit different from the metal, pure metal itself, because the particles of alloys are made up of different sizes, while pure metals are all of the same size. All the particles of pure metals are all of the same size. So if you hit the pure metals, some of the particles might slide over the others. The alloy is difficult to slide because the particles are not of the same sizes. They are not all of the same sizes. So most alloy contain more than one metal. Most alloy contain more than one metal. Some alloy contain maybe 1 or 2 non-metal that is added to maybe a number of metals. Now let's take a look at the properties and uses of alloys. Now let's first of all give 2 examples of alloy and we describe them. Brass. Brass is an alloy of copper and zinc, while bronze is an alloy of copper and tin. Brass is an alloy, brass, and bronze. There are 2 names that use most often, bronze. Okay, bronze is also an alloy. It's not an element, it's an alloy. So you know the difference. Bronze is an alloy. Stainless steel is an alloy. Okay? Pewter is an alloy. Okay? So bronze is an alloy of what? Copper and tin. Copper and tin. Okay? But why brass is an alloy of copper and zinc? Brass is an alloy of copper and zinc. So it is ordinarily stronger than the pure copper, and at the same time stronger than the pure zinc. The combined alloy, which comprises of copper and zinc, is stronger than each of the individual. Metal. Now, what do we use brass for? Brass are used for making musical instruments, like not only musical instruments, they are also used for making ornaments. They are also used for making doorknob. You know the doorknob? This doorknob. These are brass. They are made from brass. It's an alloy of copper and zinc. Why do we have to alloy metals? Allah Almighty God has given us a lot of metals on earth. We extract them. We go to part 2. We're going to describe the extractions of iron and the extractions of aluminium. Okay, which is very important for Igcse studies. So these elements on earth, we have to extract them from their ore, and then we have to make use of them after extracting them from their ore. And then the use has led us to making a better metal from the metal itself, by joining 2 or 3 or 4 metals together to make a better, based on use. If we want something harder, we join 2 or 3 metals. Harder or stronger, we join 2 or 3 metals together. We alloy 2 or 3 metals together to form a stronger or harder metal. If we want something more resistant to corrosion, we can as well join 2 or 3 metals together to produce something more resistant to corrosion. You know, iron is very corrosive. So we join 2 or 3 metals to produce something very resistant to corrosion, to form steel, stainless steel. Okay, so brass is one of those things. When we join copper and zinc together, we make brass, and we use the brass to produce musical instruments, those shiny musical flutes, and they are also used for making ornaments, the things for decorations, and they are also used for doorknobs. So that's for brass. Now let's take a look at stainless steel. Stainless steel is an alloy of iron, of course. Steel is an alloy of iron. So it's an alloy of iron, not only iron and other elements, such as chromium, nickel, and carbon. Carbon is a non-metal, but it has been alloyed with metals. But you remember, you can see that it's only carbon that is the only non-metal that is added. It's added to nickel, it's added to chromium, it's added to iron. So iron, chromium, nickel, and carbon. Sometimes we need to know the percentage of each of the contribution. So to form what we call the stainless steel. Now, a good example of stainless steel are your cutlery, your knife, your kitchen spoons, some of your pots are stainless steel, some of the plates, usually spoons. We have some stainless steel, right? So stainless steels are used for making cutleries because they're very hard, because of their hardness and corrosion. You will not want to be having a spoon. If we made spoon from iron alone, if we leave the spoon, rusting can happen to it, corrosion can happen. Why? Once the water touches it, we always wash the spoon in water and oxygen, which means air. So once they touch the spoon, all our spoon will rust. The next day, you will not want to use the spoon to eat. You see how smart the scientists were? So they say, so if we want to make a spoon now to eat, we need to find a more resistant to corrosion kind of metal. So they alloy some metals together. They take iron, blended with the chromium, with nickel, and with carbon. They produce a stainless steel. And stainless steel will not rust, will not corrode, and will keep shiny as if it's just made from the factory. Okay? Now, other alloys include iron with tungsten, extremely hard and resistant to high temperature, iron with chromium or nickel, resistant to corrosion. Aluminum with copper and manganese and silicon. This alloy is stronger but still has a low density. Okay, so these are some other alloys you find. I talked about bronze. I said bronze is what? Copper and tin. So when you join copper and tin together, copper is Cu and tin. When you alloy them together, you get what? You get bronze. Brass is copper and zinc. Brass is copper and zinc. So stainless steel you should know. Iron, chromium, nickel, and carbon mixed together to form a stainless steel. So we should know all of these things. Okay? At least very important. So the reason why we alloy always have properties that are different to the ordinary metals. One of it is stronger. They are stronger than ordinary metals. The second one is they are harder. They are harder than other metals, and they are more resistant to corrosion than other metals, and they are more resistant to extreme temperature than ordinary metals. You can see about 4 of these characteristics. They are stronger than ordinary metals, they are harder than ordinary metals, they are more resistant to corrosion than ordinary metals, and they are more resistant to extreme temperature than ordinary metals. Because they are harder, of course, they have higher temperature and higher boiling point and higher melting point. So they are more resistant to corrosion. And although these enhanced properties can make alloy more useful than pure metals. Yes, they are more useful than pure metals, right? Because they have enhanced properties. Now let's take a look at the structure of an alloy, which we've already described in our tutorial. We say for alloy, the particles are of different sizes. Pure metals, all the particles are the same size. Get this. Pure metals, all the particles are the same size. Alloy, the particles are different size because they are made up of different elements, different metals. Okay? Now, because of the combinations of different sizes of these particles, makes it very difficult for it to slide when you hit them. So when you hit them, it's different from the particles to slide. Pure metals, when you hit them, they slide, the layers slide over each other. The layers of the particles, they slide over each other when you hit pure metals. But when you hit alloy, the layers are not easily able to slide over each other. So that makes them harder and stronger. That gives them that characterizations and characteristics that makes them stronger and harder. Okay? So I think we just look at one of these things. We've already explained they have different sizes. It's difficult to distort them and so on and so forth. So with this, we come to the end of our today's class. Thank you for joining us.